In the last section, we started with polynomial functions, and we saw how you could approximate them well for x near what we were calling the center of the polynomial. So for a polynomial centered at a, so a polynomial written in terms of powers of x minus a, you can approximate that polynomial well for values of x near a by using the lowest degree terms, not the highest degree terms. The highest degree terms, like x minus a to a high power, if x is close to a, x minus a is close to 0, so x minus a to a high power is much, much closer to 0, and so it's kind of a negligible term. And so we saw that you could approximate polynomials well near their centers by taking partial sums, the sum of the first few terms starting, by first I mean starting at degree 0 and taking the smaller degree terms. One issue that arose that we looked at was that means that if you start with a polynomial written in powers of x, but you want to approximate that polynomial near x equals 2, then if your original polynomial is written in terms of x, but you want to approximate near x equals 2, you want the polynomial written for you in terms of powers of x minus 2. And so we looked at how you would rewrite the polynomial, how you would find the coefficients of a new polynomial written in powers of x minus 2 that equals your other polynomial as a function, so that you can then approximate well near x equals 2 by just using the first few powers of the polynomial written in powers of x minus 2. The method that we use to find those coefficients is going to come up again today. What we want to do in this section is approximate functions that aren't polynomials. So functions that are not polynomial functions, like e to the x, sine of x, natural log of x. We want to approximate functions like that, so these transcendental functions, by polynomials. Why do we want to do that? Well, because we understand polynomials. Polynomials are our friends. We can, by hand, we can raise numbers to powers, multiply by constants, and add and subtract. It might take a while, and you'd probably use a calculator, but you could do it by hand. And your calculator knows these simple operations of multiplying, raising to powers, adding and subtracting. And the method that we're going to use for approximating these more complicated functions is part of what your calculator does when it calculates sine of the sine of 1, the sine of 1.5, e to the 0.1. So that's what we want to look at. We want to look at writing other functions in terms of polynomials, or approximating other functions in terms of polynomials, because polynomials are very manageable. All right, so what do? We start with a function f of x. We're interested in the case where f of x is not a polynomial function. I mean, it could be a polynomial function, but we're really interested in the case where it's not. All right, but what we'd like to do, we want to approximate f of x well when x is close to some number, which we'll again call a. We want to approximate f of x well when x is close to a using a polynomial, which will be centered at a. So what does that mean we want? We want that f of x is approximately equal to a polynomial centered at a. So that's something of the form some constant plus a constant times x minus a plus a constant times x minus a squared, and so on, up to, well, the degree of this polynomial, assuming that b sub d is unequal to 0. All right, so we'd like to do this. In fact, let me call this n today. We're not really going to use n for our index on partial sums, and I like calling that n better. So we want to approximate f of x by some polynomial centered at a. How do we do this, or approximate it well when x is close to a? Well, intuitively what we do, so let me draw the graph of some function. I'm thinking of y equals e to the x, but it's kind of unimportant exactly which function this is. So here's the graph of some function. Suppose we're at some point, x equals a, so corresponding point on the graph is this. The idea for this polynomial is that, well, first you make the graph of the polynomial also contain this point, a, f of a. So we want the graph of the polynomial to include this point, a, f of a. So that means we want, when you plug in x equals a over here, you should get the same thing as when you plug in a over here. So that means you immediately get that we want b naught to be f of a. So that when x is a over here, you get f of a, and when x is a over here, you get f of a. Great, so they both contain this point. But then we also want the graph of this. The graph of this could be some curve, but we'd like for it to have the same tangent line as the graph of our original function. So I should have called this f of x, which I'm thinking of as e to the x. So we'd like for them to have the same tangent line, so that kind of, if we think of their linearization, both of them, we talked about linearization back in Calc 1, back in differential calculus. We want them to have the same tangent line, so they kind of they both kind of look the same as far as their tangents go. But then these curve in different directions. We don't want that. We'd like for their concavity to be the same. I should have said. So same tangent line means, well, we want their first derivatives to be the same. So if I call this p of x, let me call this p of x for polynomial. What I'm saying is we want the same tangent line, so we want the same slope of the tangent lines. So what we want is for f prime at a to equal p prime at a. And we'll figure out what that says about b in a minute, but we want this line. In fact, let me write this in a different way. This line says f of a equals p at a. We also want the first derivatives to be the same at a, but then we'd like the concavity to be the same. So we'd like for this to curve kind of the same way, so that maybe, okay, it has kind of the same concavity, the same tangent line, passes through the same point. But that means we'd like for the second derivatives to be the same at a. Maybe not every place else, but we have this feeling that if we force the derivatives to be equal at a, then that makes the curve look very much like, so the graph of p of x looks very much like the graph of y equals f of x near this point. And so even for x near a, but not exactly equal to a, we would expect the values of f to be close. You can probably guess what we're going to do. What you want is you want all of the derivatives of your original function and your polynomial to be the same up to whatever degree polynomial you want to use to approximate f of x. So we would need for f to be at least indifferentiable if we want to approximate by this. And then you require this. So we're going to require this and see what it makes the b's turn out to be. But the point is, by forcing the derivatives of the polynomial and the derivatives of f to be the same at a up to a high degree, you're doing your best to make the curves match as well as you can right at that point, and by controlling the derivatives, how fast the function's growing and how fast the growing is growing, and how the curves should be very close together for x is close to a. This doesn't prove that they're close, and we'll have to wait until the next section to actually get some error estimates on how to what extent making these derivatives the same forces the functions to be close together. But in this section, the basic approximation, next time we're going to look at the error in the approximation, but this time we're just going to kind of naively assume that, yes, forcing the derivatives of p and f to be the same at a, it should make the polynomial approximate the original function well near a. All right, what does this imply? When you plug in, what's p of a? Well, p of a is what you get over here when you plug in a. F of a is what you get from f. But if you just plug in a over here, all the x minus a's are 0, and so you just get b naught, which is how I originally had this written. P of a is just b naught. So we get b naught has to be f of a. All right, what's p prime of a? Well, you take the derivative of this line. So I'll put the p of x over here. So what's p prime of x? It's b1 times, so this term goes away. The derivative of this term, it's b1, plus the derivative of this term, you get a 2b2 times x minus a. The next term would be a 3b3 times x minus a squared, and so on up to plus n times bn times x minus a to the n minus 1. So what's p prime of a if you plug in x as a? Again, when you plug in x equals a, all of these x minus a's are 0, and you just get b1. P prime of a is b1. So we want b1 to be f prime of a. Well, you may have noticed this is what we got when we recentered our polynomials in the last section. We got that b naught should be the original polynomial evaluated at a. b1 should be the original polynomial, the derivative of the original polynomial evaluated at a. We are going to see exactly the same thing. We are going to get, I'll just do one more step to convince you, but what we're going to get is that the kth derivative of f at a should be k factorial times b to the k. So what I'm claiming is that the kth derivative over here evaluated at a is k factorial times b to the k. What this means is that just as in our last section when we recentered our polynomials, we get that bk is the kth derivative of f at a divided by k factorial. Right? And how do you see this? For instance, take another derivative of this line. So what do you get? You'll get p double prime at x is, we can write this, you get p double prime at x is 2b2 plus, and then you get a 2 times 3 times b3 times x minus a plus you'll get an n minus 1 times an n times a bn times x minus a to the n minus 2. And now you plug in that x is a, and so you get p double prime of a is all the powers of x minus a are 0, so it's 2b2. So yes, p double prime of a is 2b2, but we want p double prime of a to equal f double prime at a. So we want b2 to be f double prime of a. We want b sub 2 to be f double prime of a divided by 2, but it's 2 factorial, and you can see the factorials building up. Here's 3 times 2. So when you do p triple prime, you'll get that it's 2 times 3 times b3. And so since we want p triple prime at a to equal f triple prime at a, we need b sub 3 to be f triple prime at a divided by 3 factorial. So we get the same coefficients that we got in the last section when we were recentering polynomials. So, all right, we give a name to this polynomial that's coming up. So what we're finding with those bk's is that the nth order, I'm going to call this the nth order Taylor polynomial of f centered at a is, the notation is a little cumbersome. I'll put a t for Taylor, a sub f for the polynomial, the order here, an x here, and a semicolon in the center there. And what is it? It's this polynomial centered at a with the b's given by this formula. So I'll write it out with some pluses and dots, but then I'll use summation notation. So it is, we need b naught to be f of a. And then you get f prime of a times x minus a. And then you get f double prime of a over 2, but that's 2 factorial, and it's nice to start showing that pattern over x minus a times x minus a squared plus f triple prime at a over 3 factorial times x minus a cubed plus, and this goes on, plus dot, dot, dot. You would go out to the nth derivative of f at a over n factorial times x minus a to the n. All right. In summation notation, this is the sum as k goes from 0 to n of the kth derivative of f evaluated at a divided by k factorial times x minus a to the k. And this is what we expect to approximate f very well for values of x near a, at least when n is big and x is close to a. So I should say that unlike last time, in the last section, when we went out to the degree of the original polynomial, this thing with these coefficients, this recentered polynomial, equaled the original thing. If we start with a function that is not a polynomial function, this can never equal the initial function because this thing is a polynomial. And if the original thing was not a polynomial function, it can't equal it. So for instance, e to the x, sine of x, cosine of x, natural log of x, none of those are polynomial functions. They won't equal these Taylor polynomials for any fixed value of n. What we will talk about later is if you let n go to infinity, so you just keep adding and taking a limit as n goes to infinity, then those functions will equal these kind of the limits of these Taylor polynomials, at least for some values of x, but we won't get to that in this section. I should say that a couple of more things about this. In Calc 1, in differential calculus, you actually looked at the approximation. So we expect this to be approximately equal to f of x. It's what we expect. We're not going to prove anything like that in this section. We're just going to look at some numbers and what we actually get. But we expect f of x to be approximately this when x is near a. Well, you looked at this part, that f of x is approximately the first order Taylor polynomial back in differential calculus. So the fact that f of x is approximately t1, this first order Taylor polynomial when x is close to a, hopefully you remember this was called linear approximation. You're approximating this original function by some linear term. Now we're adding more terms in, and our approximation typically is much better than just approximating by these first two terms. We approximate by a higher order polynomial. There's one other thing I should say, and another piece of notation before we do an example. Our favorite place to center a polynomial is 0. We like powers of x. They look simple. When the center is 0, instead of calling this a Taylor polynomial, in that special case, it's still a Taylor polynomial, but rather than say the long phrase, the nth order Taylor polynomial centered at 0, we say a Maclaurin polynomial. So the nth order Maclaurin polynomial, when A is 0, Taylor polynomials are also referred to. Maclaurin polynomials. And the advantage to calling them this is that you don't have to say a Maclaurin polynomial centered at 0 by saying it's a Maclaurin polynomial. You're telling someone it's centered at 0, that it's a Taylor polynomial and it's centered at 0. So let's just do an example, an easy one, but an important one. So, for example, suppose f of x is e to the x. What is t in f, and I didn't write this, is also referred to as Maclaurin polynomials. And then in this case, you don't write the of a, or the semicolon with the a. Just if you leave off the center, it's assumed to be 0. So this is the notation for the nth order Maclaurin polynomial of f. It's centered at 0 because you should know that because first of all it's called Maclaurin, and secondly there's no center indicated. So what is the nth order Maclaurin polynomial of f if f is e to the x? Well, you just need its derivatives. I mean, you could go ahead and write that it's something that we can write the general form. It's f of 0 plus f prime at 0, f prime of 0 times x minus 0, so that's just x, plus f double prime at 0 over 2 factorial times x minus a, but a is 0, so just x squared, plus, I'll write another one, f triple prime at 0 over 3 factorial times x cubed, and you go out to the nth derivative evaluated at 0 over n factorial times x to the n. Great. So what's the whole problem? We have to find these derivatives of f. We know what the coefficients are. They're the bk's, what I call the b sub k's. They're always, b sub k is the kth derivative of f divided by k factorial. So yeah, what's our problem now? We have to find f at 0 and all the derivatives of f at 0. Well, that's easy. F of x is e to the x. All the derivatives of e to the x are e to the x. So the kth derivative of f at 0, well, the kth derivative of f at x is e to the x. The derivative never changes. So the kth derivative of f at 0 is always e to the 0. It's 1. So all of these are 1s. All of these derivatives. And so what we get, actually let me write it over here. So what are we getting? We're getting that if f of x is e to the x, then the nth order Maclaurin polynomial is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. That's what we're getting. This, I don't know, this both should and should not surprise you. If you recall our definition of e to the x back in differential calculus, we actually defined e to the x, the exponential function, exp of x, to be the limit of these functions. We had this collection, exactly this collection of polynomials, and we defined e to the x, exp of x, to be the limit of what you get from these polynomials. So it's not so surprising that if you then do this polynomial approximation for e to the x, you get back the polynomials that we used to define e to the x. But it's nice. It's nice that you get this, to use it as an approximation. So let's look at e to the point 1. This is equals, according to my calculator, to the full precision of my calculator display, e to the point 1 is, it is 1.105170911808. The third order Taylor polynomial evaluated at point 1 is 1 plus 0.1 plus 0.1 squared plus 0.1 cubed over 6. This is 1.1, and then this is 0.001 divided by a 2, so you get a 0.005. So we get a 1.105, and then this is 0.001 divided by 6, so we should get 1, 6 repeating here. All right, so how close? How close is this approximate? That 5 doesn't show up very well. How close is this approximation? Pretty close. We've got the 1051, and then there's a 7 here, but there's a 6, 6 here. So this is pretty good. We approximated the value of e by a cubic polynomial for x is relatively close to 0, so when x is 0.1. All right. So before I do another example of kind of this sort, I would like to introduce some formal notation where it looks like we're going to take an infinite sum. However, I just mean this as a formal thing that you can write. It's like the difference between a polynomial and a polynomial function. The polynomial is just the algebraic expression. The polynomial function is what you get when you actually plug different values of x into the polynomial. Why am I making this distinction again? Because we just had that Tn f at x is when f is, so this again is f is e to the x. Yeah, that this is this, and the n means you stop when the exponent reaches n. But, if you take a bigger n, you just go out some more. And so it's convenient just to write as a formal expression. You should think of it as t infinity f. But really, usually I just wouldn't write anything. Just this, and call it the Maclaurin series instead of polynomial. And when you say series, you're allowing that it goes on forever. So all it means is you just don't write that it's ever stopping because, I don't know, you just don't need to tell someone where you're thinking of stopping when you're going to use one of the polynomials. You just stop where you need to stop. So you have this, and you just put some dots, and you don't bother saying where you're planning to stop. But yeah, it tells you what to do if you want to take the partial sum, the first order partial sum. So you go out to the the x term, well, there it is. And if you want to take the second order Maclaurin polynomial, well, there it is. And the third order one, you take that partial sum. You just take the first few, however many terms you need, and we call this the Maclaurin series. We are not saying that this, yet, we will in the next section, we're not saying that this defines a function, that I'm not claiming that we know what it means to add an infinite number of numbers together. It's just notation, just like a polynomial. And more generally, the nth order Taylor polynomial of any function centered at A, you just don't have it stop. The sum is k goes from 0 to infinity of the kth derivative of f evaluated at A over k factorial times x minus a to the k. And you just, so this is what it looks like in summation notation. And I really would not normally write this infinity, just the Taylor series. But yes, when you want a Taylor polynomial, you stop this someplace. The series is just notation saying, hey, I know what all of the coefficients look like, no matter how far out you want to go with a Taylor polynomial. So I'm just going to say it goes on forever, and then you can decide where you want to stop. Okay, that's a Taylor series. The Taylor series. These are examples of things called power series. A power series just means the formal expression of, it looks like a polynomial centered at A, but it just goes on forever. It's a formal expression. It's supposed to be analogous to a polynomial that never stops, but there is the question of when does it define a function? When does the infinite sum actually have meaning when you plug in a value for x? A power series centered at A it just means a polynomial centered at A, but a polynomial centered at A and the polynomial never ends. So there's some coefficient plus some coefficient times x minus a plus some coefficient times x minus a squared plus some coefficient times x minus a cubed. But now you don't stop anywhere. So to know the power series, all that means is you know where it's centered and you know what the coefficients are. So saying you have a power series is really the same statement as saying you have a collection of coefficients, an infinite collection of coefficients. So the Taylor series, the Maclaurin series, those are examples of power series where we know where the coefficients that we use in the power series are the Taylor or Maclaurin coefficients, the ones you get by starting with some function f, evaluating its derivative at A, and dividing by k factorial, where k is the derivative that you're on. So this is, try not to worry about the infinite sum at this point. We are not claiming there are an infinite number of numbers that we're adding together and that we will later, we'll take limits. Right now, it's just a formal expression that means, yeah, we're going to stop somewhere when we're talking about the polynomials. We're just not going to indicate where we stop. Okay. With that notation terminology out of the way, I would like to find the Taylor series for sine of x, but centered at pi over 2. Oh, one thing I should say before I do that. If you're talking about an infinite power series like this, or you're talking about a Taylor series, then the Taylor polynomials are the partial sums. So the nth partial sum of the nth order partial sum would just mean the nth Taylor polynomial. All right, let's do an example. Let's find the Taylor series for sine of x centered at pi over 2. It will turn out that sine of x equals this once we know what it means to add an infinite number of numbers together. But right now, we're not saying that. We just expect them to be approximately equal because we're forcing derivatives to be the same. So what is the Taylor series So series just means we're going to say what every term of every Taylor polynomial looks like. What is the Taylor series of f of x equals sine of x centered at pi over 2? So not at 0 this time, just to be different. But we're going to center it pi over 2. All right? What's always true? To know the Taylor series, so the whole collection of Taylor polynomials, you have to know the derivatives of this function evaluated at your center. So I'm going to go ahead and do that first. I'm going to write down the derivatives of f evaluated at pi over 2. So if f of x is sine of x, f prime of x is cosine of x, f double prime of x is minus the sine of x, f triple prime of x is minus cosine of x, and then it comes back around. The fourth derivative of f is the derivative of negative cosine. That's negative sine. That's sine of x. Well, we're back where we started, and now all the derivatives will repeat. So the derivatives of sine are all sine, cosine, minus cosine, and it'll go sine, cosine, minus cosine, and it'll keep doing that. Well, that's nice because it means we don't have to write down a kind of an infinite number of derivatives exactly. When you plug in pi over 2, sine of pi over 2 is 1. The cosine of pi over 2 is 0. Negative sine of pi over 2 is negative 1. And cosine is still 0. So our coefficients, if you look at f at 0, f prime at 0, I'm not dividing by the factorials yet. F double prime at 0, f triple prime at 0, not at 0, at pi over 2. Idiot. Pi over 2, pi over 2, pi over 2, pi over 2. Fourth derivative of f at pi over 2. Well, what do you get? You get 1, 0, minus 1, 0, and then it starts over. 1, it'll go 0, minus 1, 0, 1, 0, minus 1, 0, and that pattern just keeps repeating. Every other term is 0, and then if you look at the non-zero terms, they go plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. So what are we getting? So we're looking at f of x is sine of x, and we are looking for the Taylor series of this f evaluated at pi, centered at pi over 2. So what you're supposed to do is take f at pi over 2 plus f prime at pi over 2 times x minus pi over 2 plus f double prime pi over 2 over 2 factorial times x minus pi over 2 squared plus f triple prime at pi over 2 over 3 factorial times x minus pi over 2 cubed. And you just go on like this. The fourth derivative of f at pi over 2 divided by 4 factorial times x minus pi over 2 to the fourth. And now I'm going to put plus dot dot dot. What is this? All right. All of the, this is 1. All of the odd terms, all of the odd powered terms are 0 because all of those odd derivatives, first, third, fifth, are turning out to be 0. So these terms go away. So we don't have that one. This is a 0, so we don't have this one. So you only get the even terms, including this is the 0th derivative of f. That's an even term. And then f of pi over 2, this is 1. F double prime pi over 2, that's minus 1. Then it goes 1, then it goes minus 1. So you only take the even terms. You have the factorials that match the power of x minus pi over 2 that you're on. But then this numerator goes plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. So what you're ending up with is you get 1 minus 1 over 2 factorial times x minus pi over 2 squared plus 1 over 4 factorial times x minus pi over 2 to the 4th. You're only getting the even number terms and the sign alternates. So minus a 1/6, 1 over 6 factorial times x minus pi over 2 to the 6th, and so on. That is what we're getting. You might find it difficult to write this in summation notation, and I will do that in a minute, but in the meantime, before we do that, so what's a reasonable approximation for sine of x when x is close to pi over 2? Well, you could approximate it, it's approximately 1. Well, yeah, because if x is close to pi over 2, sine of x is close to sine of pi over 2, because sine is continuous, and so it's close to 1. But a better approximation, that's not a constant, take this next non-zero term. So a reasonable approximation, sine of x is approximately 1 minus 1/2, 2 factorial is just 2, times x minus pi over 2 squared when x is close to pi over 2. So if we want to kind of use our calculators to see how good this approximation is, believing our calculators, what do you get? Well, let's pick an x value that's close to pi over 2. Pi over 2 is pi is about 3. Pi over 2 is about 1.5. So I'm going to ask my calculator what sine of 1.5 is. This will be equals from the calculator. I just mean equals to the display of my calculator. You need to make sure your calculator is in radians, otherwise this won't be close to correct. I did this. I plugged in this into my calculator, and it told me that sine of 1.5 is to the full display of the calculator is 0.9974994986604. Aha, yes, you probably could have guessed that. Just kidding. What do you get from 1 minus 1/2 times 1.5 minus pi over 2 squared? And now I should make a comment about this. Again, this will be equals according to my calculator. I said at the beginning of this that part of the point of approximating with polynomials is that you have a prayer of calculating the polynomial by hand. Right, it's true, but pi. Are you going to calculate pi by hand, or are you going to get that from your calculator? We're comparing the calculator answer with this, but I'm just doing that to try to convince you before we do error estimates in the next section that these approximations are good. We expect them to be good because we got Taylor polynomials by making derivatives match at x equals a. And we expect that to make the Taylor polynomial approximately equal the original function near x equals a. But if the point is to kind of get something that you can do without a calculator, pi over 2 is kind of a bad thing to have in there. So it's one of the reasons we kind of prefer Maclaurin polynomials. It's part of the reason, because at least the a isn't something unusual that you can't really, maybe you know that pi is like 3.1415, but how many places do you need to know it to? Anyway, I'm just saying it's of questionable value to approximate this by a polynomial centered at pi over 2 if your whole goal is to be able to calculate without, or approximate well without using your calculator. I also asked my calculator for this since I don't know pi to many places, and it told me that this was 0.9974939400056. How close is this? That's pretty close. We're getting the same first 5 decimal places, and then there's a 39 here and a 49 there. So yeah, the first 5 decimal places look right. This isn't proof of much of anything, and you might not believe your calculator, but it's evidence that, yeah, this approximation seems to be working okay. I do want to look at some standard Maclaurin series. It's we just did sine centered at before I do that, I said I would rewrite this with summation notation, and it's not particularly easy. It's not difficult, but you have to get used to a few things that come up when you're working with series. First of all, we only want to hit the even terms in our summation. That's not hard. You let your index go, like k goes from 0 to infinity, but then inside the expression that you're adding, you have 2k everywhere, so you only hit the even numbers. But how do you make the sign alternate? So this comes up all the time in series, or these Taylor polynomials, Taylor series. -1 to the k. Think about this. When k is an integer, when k is even, -1 to an even power, you have an even number of minuses multiplied together. This is 1 if k is even. And when k is odd, you get an odd number of minus signs, and that'll give you -1 if k is odd. So this is kind of the fundamental thing that makes that you can stick inside what you're summing to make it go +1, -1, +1, -1. Or if you need to start at -1, go to +1, just put a k +1 here. And then that'll be -1 when k is even, and 1 when k is odd. So this expression that's going plus minus, plus minus, plus minus. All right, how do you do this? You have a sum as k will go from 0 to infinity. That's not tough. And you put a -1 to the k here. Right? This will make it go, when k is 0, you get 1. When k is 1, you get -1. So if this is the 0th term, you get a +1, a -1, a +1, a -1. That's taking care of the sign alternating, +1, -1, +1, -1. Then what do you need? Then you only want to hit the even terms, so the 2k terms. So you want a 1 over, you have an x minus pi over 2 to the 2k. That makes it hit only even terms. And then the exponent on the power of x minus a matches this factorial. So if you've got 2k there, you need 2k, the quantity, 2k factorial here. And this is what we want. When k is 0, you get 1. 0 factorial is 1. This thing to the 0, it's our convention that that's 1. So when k is 0, we get 1. When k is 1, you get a minus sign. You get 1 over, when k is 1, you get 2 factorial. Perfect. And you get x minus pi over 2 to the 2. Perfect. Then when k is 2, you get -1 squared. That's +1. So the sign alternates back to a plus. You get 1 over 4 factorial. X minus pi over 2 to the 4. Yeah, this is what we want. The 2k makes the exponent and the factorial only hit the even numbers, which is what we see. The -1 to the k, not 2k, the -1 to the k makes the sign alternate, +1, -1, +1, -1. So this, in summation notation, is how you can write this series. All right. There are Maclaurin series that come up over and over again, And I want to tell you what they are, and maybe I'll work one more of them out. But they're easy. You look at the derivatives, you see the pattern, and you plug in 0 for A. Having said that, to really prove them, you have to do induction. You have to say, I see this pattern, but can I prove that that pattern always continues? We're not going to spend any time on induction in this class proving it. You'll see the pattern. It will be clear that it continues, and we won't rigorously do the induction. So I'm going to give you f. So what different f of x's should you know the Taylor series, so the Maclaurin series for immediately? Well, the ones I'm about to give you are almost all of the ones you should know, at least for now. The ones you should have memorized that you shouldn't have to do any work to figure out. There are others that follow quickly from these, but this is a nice place to start. And then I'm going to give you the Maclaurin series. So Maclaurin, centered at 0. I'm saying series, so I'm not going to say where you end. You can take a partial sum and stop at any nth order Maclaurin polynomial that you want. We already looked at this one. This one is 1 plus x squared over 2 factorial plus, and then it just keeps going, x cubed over 3 factorial. In summation notation, the sum is k goes from 0 to infinity of x to the k over k factorial. All right, what about sine of x? We just looked at sine of x centered at pi over 2. Centered at 0, it does something similar. There's an alternating plus or minus sign, and you only get half of the terms, but centered at 0, you only get the odd terms. Before we were only getting the even terms. So you get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And this keeps going and alternating. So in summation notation, this is the sum as k goes from 0 to infinity. All right, we only want the odd terms, so you'll have an x to the, we want to start at 1. So to do that, the nice way to do that is take an x to the 2k plus 1. 2k plus 1 is always odd. When k is 0, it starts at 1. That's where the x where we want to start. You always have over the corresponding factorial, so over 2k plus 1 factorial. And we need for our sign to alternate, so we need a minus 1 to maybe the k, but it's not, it is the k. It starts with a plus sign. So if you start with k equals 0, yes, you'll first get a plus, and then you'll get plus x to the 1 over 1 factorial, so this. Then when k is 1, it'll alternate to the minus sign. You'll get x cubed over 3 factorial, and so on. So you get this. Cosine. Before I say that, it is not a coincidence that sine is an odd function, so that when you replace x by minus x, sine of minus x, you can pull the minus sign out. Sine of minus x is minus the sine of x. That x is an odd function and the powers that you see here are odd. That's what happens. And if you believe that, then cosine of x is an even function. You replace x by negative x, you don't change it. You should only see the even powers here, including x to the 0, so which is 1. So this is 1, and then the sign alternates. So it looks like this, except you get all the even powers instead of all the odd ones. The sign alternates, and you only get half the terms, but you get the even ones, not the odd ones. And all of these are easy to see. Like we already did e to the x. We saw how the derivatives of sine go, they repeat after you take 4 derivatives. We plugged in pi over 2 before, but you take that same repeating 4 in a row and plug in x is 0 instead of pi over 2, and you'll see that this is what you get. And the same thing for cosine. It repeats after you take the derivative 4 times. It cycles back around. In summation notation, this is, let me see if I can spread this out some. K equals 0 to infinity. We only want the even terms. We want our sign to alternate. So that. Right, you could check when k is 0, you're getting 1, x to the 0, that's 1, 0 factorial, that's 1. When k is 1, you get a minus sign, and you get an x to the 2 over 2 factorial. And when x is 2, the sign alternates back to a plus, x to the 4 over 4 factorial, so that's what you get. This one is, it's, I don't know, it's just something to memorize. It's x minus x over 2, x squared over 2, plus x cubed over 3, minus x to the 5th over 5. What happened to 4? Sorry, there is a 4 here. You don't start skipping them. The tendency here, you're so used to factorials coming up in this subject that you're kind of tempted to put factorials in this denominator. They are not there. It's a little hard to get used to that. Nonetheless, that's the way it is. Right. Okay. And in summation notation, so I'll work this one out for you. In summation notation, this is sum as k goes from, we need to start at 1 now. There is no 0 term, and we don't even want to write 1 because you're dividing by the power of x that you see. So dividing by a 2 here, a 1 here, the x to the 0 term divided by 0. We just don't even want to start there. So you start at k equals 1, but after that, the pattern is obvious, except maybe for the minus signs. You get an x to the k over k, no factorial, assuming this is right, and we'll see why it's right. But you get this. I'm going to go to infinity. We need for the minus signs to start with a plus when k is 1. So you could either write minus 1 to the k plus 1, minus 1 to the k minus 1. Those are the same because they differ by an x minus 1 squared. Their quotient is an x minus 1 squared. So I'm just going to put a k plus 1. Right? So when k is 1, you get minus 1 squared. That's a plus, and then you get x to the 1 over 1. Then when k is 2, you get a minus sign, and then you get x squared over 2. So yeah, you get this. And finally, 1 over 1 minus x, you'll get 1 plus x squared plus x cubed plus ... And it just keeps going. What is that? That's the sum as k goes from 0 to infinity of x to the k. All right. I am going to, you just work these out. I think I'll do this one, and then we'll stop. What I want to say is that these are the Maclaurin series for these functions. Right now, in no way, shape, or form am I claiming that we have shown that they equal these or approximate these well. We're just saying we think that they should approximate well because at least near the center, so near x equals 0, because all of these are Maclaurin, so they're centered at 0, we expect these to approximate these functions well near x equals 0 because we forced the derivatives to be the same. And I mean the polynomials that you get by truncating anywhere. So the partial sums of these series, you expect them to approximate those functions well near x equals 0. In fact, at least what we will see later when we talk about infinite sums is that is that once we make sense of the infinite sum as a function, that this function equals this for all x. And this function equals this for all x. And this function equals this for all x. These two, these will not equal these functions for all x, but for some x. This function will equal that one for all x between 0 and 1, where you, between negative 1 and 1, where you can't include minus 1, because that would give you a 0 here, but you can include plus 1, which would give you the natural log of 2 here. So yeah, this will equal this for x's between minus 1 and 1, and not including minus 1, but including plus 1. And this will equal this for all x's between minus 1 and 1, where you can't include either minus 1 or 1. We'll see that later. But right now I just want to emphasize, we're not looking at these as functions. We're looking at these as formal expressions, just that we're interested in chopping off somewhere to get the Taylor polynomials or Maclaurin polynomials and using them to approximate near the center. Yeah, and we're certainly not saying that they equal the functions that we started with, although we'll see that that's true for some x's later. All right, let me work out the Maclaurin series for natural log of 1 plus x. And then we'll stop. So suppose f of x is the natural log of 1 plus x. The coefficients in the Maclaurin series, so tfx, the sum is k goes from 0 to infinity. I don't care whether you write b or c sub k, but the coefficient in front of the x to the k term, so a is 0 here because we're talking about Maclaurin series. B sub k is just the kth derivative of f evaluated at 0 divided by k factorial. So the problem is kind of what the problem always is if you're trying to find these coefficients, that you need to find a formula for the kth derivative of f at 0, or in general at a, for a Taylor series or for the Taylor polynomials, but we're looking at Maclaurin centered at 0. So we need to look at f, we need to look at its derivatives and see if we can find a formula, kind of the pattern in fk0. It's not bad. F prime of this, the derivative natural log of something. You get 1 over something, but then by the chain rule, you have to multiply times the derivative of the inside function. But the derivative of 1 plus x is 1. So this is the derivative. Let me write it as 1 plus x to the minus 1. You could plug in 0 now, but let's just calculate the derivatives first with x's in them, and then we'll plug in zeros at the end. F double prime of x. How do you differentiate this? The minus 1 comes down. And then you get, so we do the power rule. The minus 1 comes down, you subtract 1 from the exponent. You have to multiply times the derivative of the inside, but that's another 1. So you get this, f triple prime. You differentiate again using the power rule. You get minus 1 times minus 2, so you get 1 times 2. The minus signs cancel. Plus times 1 plus x to the minus 3. And you keep going. The fourth derivative. You get a minus sign because you've got this minus now, but then aside from that, it's 1 times 2 times 3. You get a minus 1 times 2 times 3 times 1 plus x to the minus 4. I'll do one more. The fifth derivative of f. You get a minus minus, so that's a plus. Then you get 1 times 2 times 3 times 4, so we're getting a factorial, times 1 plus x to the minus 5. All right. So what are we getting for, I'm not going to ignore this factorial down here, but right now I'm just worried about, do we have a formula for the derivatives of the f's So what's f of 0? F of 0 is the natural log of 1 plus 0. Well, that's the natural log of 1, and that's 0. Okay, that's fine. But then, what are we getting? We're getting f prime at 0 is just 1 to the minus 1. So that's 1. F double prime at 0. Every time we plug in 0 into one of these, we're going to get 1 plus 0 to this power. So that's just 1. So what we're getting are the coefficients in front of here. So f prime is a plus 1. F double prime at 0 is minus 1. F triple prime at 0 is 1 times 2, so it's 2 factorial. The fourth derivative of f at 0 is negative 3 factorial. The fifth derivative of f at 0 is positive 4 factorial. I hope you see what's going on. It's every time you take another derivative here, you'll get a factorial because you get 1 times 2 times 3 times 4 times 5, but you keep getting a minus sign, and you get a minus times a minus, so that turns into a plus, but then the next time the minus shows up. So you're getting this alternating sign of plus minus. This one doesn't fit the pattern. This one starts out as 0, but after that, this is 0 factorial. So 0 factorial is 1. This is minus 1 factorial. Then there's 2 factorial, minus 3 factorial, plus 4 factorial. The next one would be minus 5 factorial. So the sign, aside from this first term that's 0, kind of 0th derivative, you're getting alternating factorials. So what are we getting here for the kth derivative of f at 0? So I'm going to do this when k is not 0, because that one's just not fitting in with the pattern. So as long as k isn't 0, what we're getting is, so if you look, you're on 1 less factorial than the number of derivatives you've taken. So if the number of derivatives is k, you're on 1 less factorial than that. So this is k minus 1 factorial. Right? So for instance, when you're on the 6th derivative, you've got 5 factorial. We still have to divide by this k factorial. And now we need to make the minus sign do what we're seeing, which is alternate. Okay, so that's a minus 1 to the something, and it's going to be k or k plus 1 or k minus 1. It's when k is odd, you get a plus, and when k is even, you get a minus. So you can put k minus 1 or k plus 1 up here. It doesn't matter which. So I'll put a k plus 1 so that when k is 1, you get minus 1 squared. So that's plus 1, 0 factorial in the numerator, and then you're dividing by 1 factorial down here. But this numerator is matching these derivatives that we found. So for instance, when k is 5, right, you should have the 5th derivative of f at 0 in this numerator. When k is 5, we get minus 1 to the 6th. That's positive. And 5 minus 1 factorial, that's 4 factorial. Good. That's this. So this is what we're getting for bk. This. So what? What does that tell us? It tells us that if f of x is ln of 1 plus x, then the Maclaurin series for that looks like, to avoid this problem when we're on the 0th term, we'll just start at k equals 1. And that'll just immediately leave off the x to the 0 term, and we won't have to worry about the fact that this didn't fit into our pattern. It doesn't fit into this formula. So after that, we would just put in that bk times x to the k. And this should be our Maclaurin series. Now, this isn't what I wrote over there. I started at 1, that's true. Before, we had the minus 1 to the k plus 1. We had x to the k, but in the denominator, we didn't have this k minus 1 factorial in the numerator. And in the denominator, we didn't have a k factorial, we just had a k. So what's going on? Well, in addition to making signs alternate by taking minus 1 to the k, another trick or thing, another property, algebraic property that comes up over and over again when you're working with Taylor and Maclaurin polynomials and series is how factorials work. So we're getting that this is, the sum as k goes from 1 to infinity of minus 1 to the k plus 1 times k minus 1 factorial over k factorial times x to the k. But the good news is that k minus 1 factorial divided by k factorial simplifies and is 1 over k. Why is this? Don't think that somehow magically these exclamation points cancel. That's not what's happening, and it wouldn't give you this even if it were what was happening. You have to think about what factorials mean. You don't just get to make up rules. Factorial, k minus 1 factorial means you start at k minus 1, and then you multiply all the numbers less than that together until you get down to like 3 times 2 times 1. That's what k factorial means. You take all the integers between 1 and k minus 1 and multiply them together. K factorial means a similar thing, but you start at k and then you take all the numbers less than k and multiply them together until you get down to 3 times 2 times 1. Well, but all of this stuff cancels. This k minus 1 factorial is exactly what you're seeing right here. And you can cancel that with this, and what you end up with is that this is just 1 over k. This is a particular way of writing the iteration formula that defines factorial. If you cross-multiply, well, what this says is that, and you can use this as a way of defining factorials, k factorial is just k times k minus 1 factorial. So that if you divide both sides by k factorial and divide both sides by k, you get the identity that we're writing, that k minus 1 factorial over k factorial is 1 over k. That means this simplifies to what I wrote before for the formula for the Maclaurin series for the natural log of 1 plus x, because this over this just simplifies to 1 over k, and so we usually write this as x to the k over k. And then you can write out the terms and see that it's what I wrote. When k is 1, you get a plus sign, and times x over 1, so you get x. When k is 2, the sign alternates to a minus, and you get x squared over 2. When k is 3, you get x cubed over 3. When k is 4, the sign alternates. You get what I wrote. All right. And if we wanted to approximate the natural log of 1 plus x when x is close to 0, it means if we were using Maclaurin series, which would work fairly well, that we would say the natural log of 1 plus x is approximately, write out as many of the terms in the Maclaurin series as you want. It starts out as x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Stop there. Say it's approximately this 4th degree polynomial if x is close to 0. How good is this approximation? Well, we could pick a particular x value that we are calling close to 0 and get out a calculator and calculate both sides, or really we could do this side by hand if we pick something like 0.01. This side you probably can't do by hand. In fact, when I'm asked to calculate functions like that by hand, of course I use the Maclaurin series. and estimate. We could get out a calculator and do this, but we still wouldn't know. We wouldn't know how close x has to be to 0 to make this approximation to be within some desired accuracy that we want. And it's what we're going to look at in the next section. This was just getting you used to notation and terminology. And the idea of approximating by a polynomial that whose derivatives you force to be the same as the derivatives of your original function at the point A. In the next section, we're going to look at the error associated with this, and we'll be able to prove that, oh, if x is this close to A, then if you go out this far, you can guarantee that your error, no matter which x you've taken in the specified range, that's close enough, so that your error is no worse than this. So that's where we're headed. That bothers people more than kind of this section where you just calculate Taylor polynomials and Taylor series, Maclaurin series, but it's an important topic, and we'll have to do it.